Now that we've talked about slope, we can take the idea of the slope, we can actually apply it to any function that we want. And when we do that, we would be talking about an average rate of change of that function, to be official, with respect to x. So function values or y values, change in y over change in x. And we would want to know about our x changing from one value, x1, x sub 1, to a second x value, x2, x sub 2. So we are preserving the same order on the top and on the bottom as what we did with slope, function values or y values. So same. But because we're talking about any function whatsoever, we're not describing the function itself because of this calculation. We're only talking about an average rate of change. We can set it up as a final value, second value, minus initial, first value. As with slope, we can also change the order as long as the order on the top is the same as the order on the bottom. So initial value, first value, minus final value, second value. We can set it up however we choose. So we got an example here where we just use this exactly as it looks, find that average rate of change of capital G of x from x equals -2 to x equals 1. We've got our rule for G of x, so we can calculate those values. We can do the final minus the initial, the final minus the starting. Function values down on the bottom, final minus starting initial x values. So we put in those function values that we calculate. We've got our x values on the bottom that we're subtracting, simplify, and what we'd be saying is no matter what this function looks like, from x equals -1 to x equals +1, that function has gone down 4, right 1, starting with the x equals -2, ending at the x equals 1. So if we connected those two dots together, no matter what that function looks like in between those 2 points, we've got that line that has this particular slope connecting those dots together. It's a very, very rough approximation of what we can say about that function. The interesting thing is, the closer that these two become, the closer that line would match up with the appearance of that function. So we can kind of use this idea as a way of saying, how is that function behaving? And if we look at small enough little chunks, that might be a pretty decent sort of way of talking about how that function is changing as we move in little tiny pieces. This is something that you'll hear about again if you go far enough in math. One of the places where we find this idea to be much more useful would be like this next example here, where we're talking about something that we can all get behind, speed. Find the average speed. If you travel from mile marker 101 to mile marker 351 between 12:30 and 3:10. Okay, well, cool, man, I can do that. I don't necessarily need some sort of wild thing. The point kind of is that that's an average speed. Like at any given moment, like at 1:12, you could be going faster or slower than that average speed. But over that entire time frame from 12:30 to 3:10, on average, how fast are you going? So you could be slowing down and speeding back up again, slowing down and speeding back up again, over and over and over again. You don't necessarily need to be going at that same average speed every single second of every single minute during this entire time frame. It's just an average. So again, usually what you've got going on is this final minus initial sort of thing that you see us doing in these examples. That's much more commonly the case, kind of following along with basic science. Final minus initial, position. That would be the distance that we travel. Final minus initial time, that would be the time elapsed. That's the normal stuff that we talk about and think about when we talk about speed. But this is an average speed, so we have that change in position over top of the change in time. So the top is nice, we calculate that out pretty quickly. The bottom, as far as everyday stuff, 2 hours and 40 minutes, that's not really the way that we would want to use that value in order to get that final answer. We're used to speed being miles per hour. So we need to change 2 hours, 40 minutes into purely hours. So the 40 minutes needs to be converted over into hours. 40 minutes is 2/3 of an hour. So down on the bottom, 2 2/3, that's still not very convenient. So scrap the mixed number and do the fraction version instead. And then, hey, instead of dividing by the fraction, keep change flip, keep the 250, change this to multiplying by the 3/8, and we would get, 93.75 miles per hour. Somebody's speeding, or somebody's on the Autobahn. But again, that's an average speed. So at any given moment, somebody could slow down all the way to 70. Somebody could speed up all the way to 120. It's just that over that entire period of time, that was the average speed. So if we smooth out all of those imperfections of speeding up and slowing down, if we just smooth it all out, 93.75 miles per hour. We can take the idea and the formula, and we can make a bit of a tweak and get something that is much more convenient to us later on in math. It's something that we can talk about a little bit right now, and we can work through the algebra and the simplification process. But this business is much, much more powerful when we get some more math under our belts. So for those of you who have to eventually go as far as calculus 1, you're going to see this again. The difference quotient. Fancy name for basically doing the same average rate of change as we have already been doing, but we generalize it. So instead of this x1 and x2, we just kind of say, let's just call the starting place very broadly x. And let's say, x. And let's say that we're going to travel a certain amount. So we're going to have a change in the x value, change in x. Now we've got a much broader kind of definition of what's going on, and that also allows us to simplify that denominator. If we talk about that subtraction business from the rate of change expression, and we use x plus delta x minus x, well, those x's are going to cancel out and just leave us with that delta x, that change in x. But even that's a little annoying, so as far as math people go, why say delta x, two symbols, when we can streamline that just a little bit? Let's just use a letter that we don't necessarily have often appearing in another sort of way. Let's say x plus a little tiny bit that we'll call h. That way that denominator, instead of being that delta x, is just h, one symbol, kind of streamlines things. Still the same idea. These are both the difference quotient. Again, algebra, we can work out. We can take our function and plug in this x plus h. So going back to that capital G function that we had mentioned in the earlier example, we can take that function and plug in this x plus h. Instead of the x, x plus h gets squared. Minus 3x, nope, not anymore. Instead of the x, it's this x plus h. Plus 2, minus the original function. So minus the original function We can clean that up. We've got the algebra skills to do that. We can multiply, we can distribute subtraction over here, we can combine like terms, and we can come up with a nicer, shorter numerator. But we've got that h on the bottom, and so it's always nice to know, is there something that we can do with that? And as it turns out with the difference quotient, we should always have some sort of way. Sometimes it's very direct, sometimes it's much more subtle, much more clever, how we can eventually reduce out the h that's on the bottom. But we must be able to do that. It's one of those nifty, quirky little things about the difference quotient. Up here on top, I got an h, I got an h, I got an h. I can just factor an h out to the front, and then, hey, I can reduce that out with my h on the bottom. What this gives us is a generic version of the average rate of change. And we can pick our starting place. So in that earlier example, we had said, hey, we're going to start at x equals -2. We can pick how far we're going to go. And in that original example, we said, well, we're going to start at x equals -2. We're going to end at x equals 1. That would be a change of 3 units. So we can plug in the -2. We can plug in the 3. Hey, look at that. 2 times -2 is -4. Plus 3 minus 3, that's the -4 that we got earlier. But now we've got an expression. It doesn't matter where we start. Do you want to start at x equals -10? Instead of going 3, do you maybe only want to go 2? Instead of going 3, maybe you want to go 5. It doesn't matter. We've got an expression. We can pick wherever we want to start and however far we want to go, and we can calculate that rate of change lickety-split. And that's kind of what that difference quotient is allowing us to do. And again, the interesting thing for us as we get far enough in math is to say, what's going to happen if that span of x from start to finish gets smaller and smaller? So what if the h gets smaller and smaller? Those x values starting and ending x values get closer and closer together. That difference, that h, gets smaller and smaller, gets closer and closer to 0. So it's a little bit of where that can go once we've got enough foundation to be able to handle that sort of thing and really get the full effect out of that difference quotient. For now, it's just enough to say it gives us that average rate of change in a very generic sort of form, and I can pick the starting value that I want, and I can pick how far I want to go along the x, and this will automatically crunch out that average rate of change.